Okay, so bonjour à tous. Good afternoon. So can you hear me correctly? Yes? Okay, good. So, well, let's wait for the person late to sit. So my name is David Clément. I work at Institut d'Optique, which is in Palaiseau, so it's like something 20 kilometers south of Paris. And so I will have the pleasure to give you a few lectures on optical lattices, which is rather quite a broad topic in our community. So there are several things that I will not treat. And actually, I expect some of these things which I will not treat to be treated next week. But this you will be able to tell me at the end of next week. And so just to start, to put these lectures in a modern context, well, I was thinking about how to start with. And then I went on the website of the quantum flagship, which I've never did before, and I saw that. So I thought, well, okay, let's start from that. Even though the past is somehow also quantum, because we already have computers and things like that, which or lasers, but still. Okay, so the future is quantum, and actually I'm a bit joking, but you may have heard about this thing, which is, so it's a European project, which is called a flagship. So before there used to be something on the brain and something on graphene, and so now there's something on quantum technologies that started a few years ago. And not only at the European level, but also at national level in the US, in China, in France, in Germany, there is this tendency to invest for the development of quantum technologies, with typically 4 ideas, which are the following ones, so the so-called 4 pillars. Quantum computation, well, building a quantum computer somehow. There are many different ways of building such a computer and different type of computers, but the idea is to be able to do calculations, of course, which perform better than classical ones. Quantum sensing, so to be able to measure interesting quantities, once again, better that we can do this at the time. The quantum simulation, which is the idea of actually trying to solve in experiments some hard problem to solve theoretically and get some answers, and also to communicate using quantum means, which has certain number of positive properties. So what about optical lattices in there? Well, typically there are 2 things where optical lattices can be useful, so quantum simulation and quantum sensing. And actually, you've already heard about the aspect of sensing metrology. On the one hand, you have heard with Franck that one can build atom interferometers to make interesting measurement. And that actually you have these optical lattices which are used in order to to create beam splitters and mirrors for atomic matter waves. So this is one of the, let's say, use of optical lattices. You've also heard about this, let's say, strontium clock at Gila, which Anna-Maria Rey has been discussing, where strontium atoms are located in an optical lattice. So we will discuss a bit of beam splitters and mirrors today. We will slightly touch on this in the 3rd lecture. And as for metrology, I will also mention the possible use of so-called block oscillations to measure some quantities, especially some forces. Great. So this is what kind of thing optical lattices can be useful for in metrology. And I told you that it's also interesting in the simulation context. So there the situation is a bit, the motivation is a bit different, but it's basically trying to build a crystal. And it's about building a crystal of light for the atoms. So what we will be discussing a lot is this configuration where I send 2 light beams contrapropagating, assuming that they are phase coherent, so that they can interfere, and they create this stationary intensity potential. And as you can guess already from Franck lectures, this creates a dipolar potential. And so therefore the atoms see this lattice structure, which mimics the one you may have in a solid. Actually, it rather mimics a perfect lattice, while in a solid you will have defects, phonons, and so on. And so for that, we will discuss in the second lecture that we have bands, similarly to a solid, and that we can play with that. So what it is useful for, it's useful to simulate things that one cannot calculate. And so without interactions, all these problems, we can solve them. So of course, we will put interactions. And somehow create or simulate what we call correlated matter. And I will tell you a bit more what I mean by correlated matter in the following lectures. And so typically in lecture 3 and 4, we will address this type of questions, which is, well, I have this lattice structure, which is a crystalline-like structure. I put particles in it. They interact. What happens? And typically what you have, just like to sketch a picture, if you put your atoms, let's say there are green and red atoms in this case, you have the atom in this optical lattice. So if it is located in one lattice site, it may tunnel from one side to the other with some, let's say, energy scale J. And this is kind of analogous to having an electron that jumps from being close to an ion to the next ion. And of course, 2 atoms may interact on the same site, which is once again kind of mimicking interactions that you may encounter between electrons in a solid. So as I said, the typical ideas that are behind this quantum simulation is to better understand some, let's say, basic quantum phenomena. In particular, when you put quantum fluctuations, interactions, there are many interesting things that happen, but which are also very difficult to tackle. And especially, it may lead to phase transitions or to magnetism. And so therefore, I will just try to illustrate a little bit in this third and fourth class the type of questions that we are trying to address, and where we are, and what type of, let's say, open questions are still present. Okay, so this was to introduce the general scope of these lectures and to put them in this context of quantum technologies. So this is the program, or kind of tentative program. I don't exactly know how much we will go through those things. We will see. It depends also on you. Well, I mean, do not. I mean, please stop me as soon as you have any questions. So, and of course, I mean, how often you stop me will change the pace. But so today it will be really really easy. I will start by some reminders on light shifts. Introduce optical lattices, discuss a bit about geometries, and discuss what happens when we are just using an optical lattice for a very short time. In the second lecture, we will go towards stationary optical lattice, so start talking about bands, and discuss a bit what happens typically without interactions, a few effects which are interesting in this context. And so, as I said, the third and fourth lecture would be about interacting atoms. So first we will start by interacting bosons, and then we will end by interacting fermions. So I hope I will have some time to speak a bit about fermions. And typically, you will see that what will be the end of this class about fermions should naturally open the lectures that you will have next week about magnetism. Okay, so this is the plan. It's the first time I'm giving lectures at this kind of lectures with doctoral students. So, well, we'll see. I don't know exactly how fast I should go, so please stop me or tell me that I'm not going fast enough, and then we will see how it goes. Okay, so it's fine. Well, this was kind of just broad context. So let's start with the first introduction. And what I would like to start with, do you see in the back, or do you want me to switch on the light? It's fine like that? Okay. So what I would like to start with is just a reminder on light-atom interaction. So you have already discussed that quite a lot with Frank. And so therefore I will not spend a lot of time. So what I mean by that is that I have somehow an atom and I have some, let's say, a laser light. And this is the system I'm interested in. And you have seen with Frank that typically there are two types of forces that we can derive for such interactions. You have one which is conservative, and you have one which is dissipative. So the conservative one, how does it occur at a microscopic level? It's about absorption and, sorry?
Emission.
Oh, well, which one?
Stimulated.
Yes, thanks. So this is absorption and this is stimulated emission. And if you have stimulated emission, you emit a photon in the laser field. So, I mean, there is nothing that exits this system, right? On the other hand, if you do absorption and spontaneous emission, then you emit photons in modes which are not that of the laser, and I mean the system loses some energy. Okay, so I will basically always have in mind when I will talk about my atom, I will have in mind a two-level system. So this is, of course, easier to work with. But I would like also to insist on the fact that it is also very true, in the sense that you have seen, for instance, with Anya Maria Ray this morning, that if you play with the atomic structure, well, you can isolate a two-level transition, right? So for instance, this morning she was showing us that she would be lying in the -9.5 state, and this would be only coupled to the upper state, and all the other degenerate states would not be coupled. So it's not something just completely for pedagogical reason. It's also something that we can do in the lab, just because we know how to play with the atomic structure and isolate some optical transitions. Good. So we will have this two-level system. So typically I will use this all the time. And what I will be interested in is mostly, of course, this conservative part, where you can write the force as the derivative of a given potential, right? Just because it is conservative. Okay. Well, by the way, I don't know if Frank made this comment. Do you know, I mean, do you have an intuition where the force is coming from in being conservative? How I can, let's say, if I just think about exchange of momenta? Like, let me ask the question the following way. I put a light like that on my two-level atom. How do I understand that there is a force which is conservative? Well, imagine this is, let's say, K1. This is K2. I absorb in K1, so I get this recoil. And I emit in K2, so I get this recoil. And I have a delta P here, which is non-zero. Okay? So from that, you also see that if I give you a plane wave, what is the conservative force? 0. Yes. So have these kind of pictures in mind. Well, actually, always in all the class, we will be always referring somehow to we are exchanging a momenta with a light. It's always a two-photon, so absorption, stimulated emission. And so, well, no conservative force if you have a plane wave, of course. And so we will always deal with at least two plane waves or some curved wavefront. It's fine? Okay. So now I would like to remind you, like a different way of what Frank has done, to let's say know what is a light shift. So I have my two-level system, and I'm shining a laser. Let's say that it's detuned by a quantity delta, for instance, with a Rabi frequency omega, right? The Rabi frequency is minus dE over h bar, where E is the electric field of the light and D is the dipole of this atomic transition. And so I would just like to get the light shift in the dressed atom picture. And the reason why I would like to do this is just because it's easy to get what is the light shift. And then second, because it's nothing but second perturbation theory, which we've heard about Anya Maria Ray this morning. So this is another example, and we'll see another one in the class. And I think having in mind how to derive just such quantities by second perturbation theory, it's always good. So it's kind of, let's say, attitude that you should get. Okay, so I will assume that I have typically n photons, or rather that, let's say the following. So I'm interested at the state where the atom is in the ground state and there is n photon in the laser mode. So this state, to which state is it coupled? By the light? Yes. En minus 1. And when I do stimulated emission from the E, I also get back to that. So since I'm considering only the conservative force, this is the two states I'm interested in. So the energy of this guy, it's Eg plus, let's say, n h bar omega. The energy of this guy will be EE plus n minus 1 h bar omega. Well, let me call this E1. So this will be E2. And so if I want to write this as a function of E1, so I have EE minus EG. And no, minus h bar omega. It's the minus 1 here. And so you see that this is h bar delta, the detuning. Okay, so I have this. Actually, what I could do is I have this Gn, which is separated by En minus 1 by a quantity which is as h bar delta. Well, it's in one direction or the other. And so this is the dressed states. Actually, it's there is not much of a space. Yeah, or I will do the following. No, because then I will be always just like canceling what I'm writing. Okay, so now what I would like to do is to write the Hamiltonian. And so what I can do is to write the Hamiltonian by, so I will put the, so what I want is to have this symmetric Hamiltonian. What do I need for that? So the Rabi frequency is omega over 2. This is fine. This is just the coupling of the light. And then I want to put energies at half distance between these two states, right? To have here. So this is, I will call this energy epsilon n. So this, of course, you can write it directly from E1 and E2. Okay, so this is one way I can write the Hamiltonian. And the good thing is that this is really easy to diagonalize. Well, to get it diagonal. And to get the eigenvalues, which are nothing but epsilon n plus or minus h bar 2 square root of omega square plus delta square. Okay, so for the moment, this is, I've not done any approximation, but now we'll do an approximation. And the approximation I will be doing is to consider relatively large detuning delta. And if I consider this situation, which is, by the way, similar to saying that I will be very much detuned, we will come back to that, in order to avoid spontaneous emission and to really consider only this conservative force, then I can develop this part here, right? So this is perturbative solution. So you know how to get it. It's epsilon n plus or minus. So I have h bar delta divided by 2 and 1 plus omega square divided by 2 delta square. Something like that. And so what do I get? I get that I have these states which are shifted by a quantity which is omega 2 over 4 delta. And so this is the light shift. So now, in practice, what I will be doing, well, I have my atom in the ground state. I shine some light very far detuned. And what I will get is a light shift for the ground state atom, so which is corresponds to a dipole potential, which is omega 2 over 4 delta. Okay? So this, I think, you have already seen it with Franck. Maybe from a slightly different approach. So, of course, I mean, behind writing this non-time-independent Hamiltonian, you have a rotating wave approximation and so on. So I have not developed all these things, which I guess you already kind of know. But you see, knowing that the time-independent Hamiltonian writes delta omega omega minus delta over 2, this is kind of something you should almost know by heart. And if you know that, then it's just completely easy to get the light shift again. And by the way, so we have a coupling which is omega, well, actually omega over 2. And so this is, this you can also view it as the second order perturbation on the energy, because the first order perturbation on the state G and E is to add the value of the laser, so n times h bar omega here and n minus 1 h bar omega there. So this is the first order correction to having the light. And the second order correction is this coupling. And so this is, let's say, the coupling between Eg square, well, the coupling of the light state, divided by the difference in energy between the two dress states. So we will be working with that. Which, yes, also this right, also 3pc square divided by 2 omega naught to a third power, gamma divided by delta times the intensity of the light. So if you want to write it in terms of light intensity. Well, omega naught here is the Bohr frequency. So it's h bar omega naught, it's the difference between the bare atomic states energy. So, right, it's fine. I told you we would be starting really slowly. Yeah? But once again, keep in mind this type of typical approaches. I mean, the non-time-independent Hamiltonian for the conservative part, the unitary part of the light-atom interaction, write this way, and then I can easily get to the light shift. Okay, so of course where is it? Actually, it's funny because I intended starting showing a slide, so it woke up. Good. So the one thing that, of course, one should be very careful about is that in this derivation, I made some approximations, and actually a correct derivation is not only this, as you can see, but you have two terms, a resonant one and an anti-resonant one. which are okay. I've not done it, but and this term is most of the time completely negligible, but sometimes it's not fully negligible. So it's easy to put it when you do some numerics to make sure that it is indeed negligible. So from this respect, I strongly advise you to have this paper always around with you. It's old, I mean, it's from the 2000, but you have the most useful equations which are derived to, let's say, calculate optical dipole traps. And I think you already given this, these references. We all like and share this reference. Okay. So this was for the dipole part. So what is done in this reference as well is to calculate the scattering rate, which I did not do. And, well, so it takes this form. And as it was shown by Frank, that if now you have a detuning which is, let's say, small compared to the Bohr frequency, you can easily write the ratio between those two quantities in this way. So the scattering rate is proportional to the dipole potential times gamma over delta, where gamma is the lifetime of the excited states. And so, of course, if the detuning is very large compared to the lifetime of the upper state, then we can neglect the scattering processes, and we will only consider the conservative trap. So from now on, I will assume that there are no spontaneous emission. Once again, it's exactly like this term here. Keep in mind that although we can easily make this approximation, it turns out that you also often need to account for it in experiments. So once again, I mean, it's easy to plug the numbers, at least numerically, for the situation you want to describe, before just saying, well, this term is completely negligible. So it's a good attitude to keep it in mind. Okay, so for me, it's fine for this reminder on light-atom interaction. Do you have any questions? Yeah.
The first two atom level that you put, like just E and G for the excited ground level, it's when you don't have any. I mean, it's just the atom without interacting with light, and then when you put the G with N photons, it's like before the photons interact with the atom, or
it's when I consider, so just the atomic state Eg, it's just like the internal structure of the atom, and then I put some light on, okay? And the very fact that there is some photons, this changes. Then I'm considering the state of the atom plus the light field, okay? When we do this kind of dress test picture, of course, you have many other states. Because here I'm just drawing like Gn, but there is Gn minus 1, minus 2, and plus 1, plus 2, and, as many as you want. Okay?
with respect to the first atom level, where these levels are placed?
Upper.
Huh?
Their energy is it's that of the atom plus n times the energy of a photon.
Oh, okay.
You know, at some point, I think I wrote that the energy of this guy was the energy of the atom plus n times that of the photon.
Yeah.
Okay. And so if you have spontaneous emission, this one can decay to the state which is Gn minus 1. Right? Because if it gives this photon to a mode which is not that of a laser, I'm still having minus 1 photon and the atom is in the ground state. This would be spontaneous emission, which would couple so the different, let's say, states that I'm considering here. But since I said, well, only the conservative part. The conservative part only couples these two guys, and that's it.
So the part on the right is like before they interact, and the part with the light shift is
Yes.
after the interaction.
Yes. You know, when you do second order perturbation theory, you always get that. So I have the atom and I couple it to some light. So the first correction is the energy of this new system when the first one is in the state I'm considering. So this is the first order correction. So in that case, it's n times h bar omega. And then the second order is the correction in energy which corresponds to the coupling. So this is why I'm saying that this corresponds to second order correction in perturbation. Other comments, questions? No? Okay, good. So, well, let's describe an optical lattice. So this is an interference effect where I'm shining two beams. So let's say one beam with a frequency omega 1, a phase omega phi 1, and a wave vector k1, and a second beam k2. And I will take that the wavelength of the two lasers are relatively close, and so I will call those two wave vectors k. And so what happens is that if your two waves are phase coherent, then you have some interferences here. And I can, so let's say that I will call this x. Then along this direction, how can I get what is the pattern of the interferences? Well, it's kind of easy. You will have a phase. I mean, you will have a phase associated to this first beam here, which will be. So of course I have omega 1t. I have the phase phi 1, and I will have so a projection. So I need to put a theta. I will have k x sine theta. And for the second one, I have, of course, omega 2 phi 2 minus kx sine theta. I take a symmetric configuration because it makes things easier. And so these two terms interfere. And so what I will get a 1 plus this term minus the phase of this one, and vice versa, which gives me a cosine of their differences. So I have 2kx sine theta plus omega 2 minus omega 1 t plus phi 1 minus phi 2. Okay, this is just usual interference terms. And so if I write the detuning omega 2 minus omega 1 small delta, what I can do is then write the potential as V naught. So the 1 plus cos, I will write it as a sine square. So kx sine theta plus delta t plus, let me write this delta phi. Okay, and so this is our optical lattice. So, well, what is important? What do we will need in the following? So the first point is that we will need an energy scale. So what we will be using as an energy scale will be the recoil of a photon and I will often write the amplitude V0 as S times the recoil and use this S number as the lattice amplitude. Of course, well, recoil energies, they are typically, let's say, kilohertz. Well, it can be less than a kilohertz or even 20 kilohertz if you work, for instance, with a light atom like metastable helium. But you always need to keep in mind, I mean, this is a crucial quantity when you will be treating a problem or doing an experiment. This is an energy scale and an associated time scale, of course, that you need to know. It's really important. Well, the second thing that one can say, well, by the way, of course, we see that if this phase difference would be fluctuating a lot, I mean, we would be washing out part of this in interferences, right? So we don't know, this is why we want the lasers to be relatively phase coherent together. So the second part which is interesting is that you have these terms, this term delta t. And so you see that this means that if I have a detuning between the two beams, then this corresponds to a lattice which moves. So if delta is different from 0, then you have a moving lattice. And so this can be used in different situations, and we will see something, one example of using such a moving lattice by the end of the lecture. And of course, last but not least, you have this lattice spacing, which is lambda over 2 times sine theta. So this is the energy scale you should know, and this is the length scale that we will be using a lot as well. Okay, and so I repeat again, one of the pictures that you should keep in mind is the fact that, so I have these two beams that interfere and create the lattice I'm interested to realize. And what happens is that I will have one atom, let's say in my ground state, with a given momenta initially. And this atom does a 2-photon transition, absorption stimulated emission, and end up picking up a momenta. Okay? So this, and so this is, we said this is for detuned. So we will use, and you will see that this, this story of the momenta to which we are coupling will come often in the class. So the simplest situation, what it is, it's the one I've shown before. if you make the two beams counter-propagating, then sine theta is 1. If they have no detuning, delta is 0 and no phase difference. And so you are left with sine kx squared. So this is the simplest situation. And as I mentioned in the introduction, we do create a periodic structure, which is kind of crystalline-like structure. But really, one of the things which is one advantage of working with such a light crystal, or a crystal of light, is that it is perfect. I mean, you really realize that because you are working with light interferences, this is a perfect light intensity distribution, perfectly periodic. Well, okay, of course, if now you would enter the detail of experimental realization and consider that you have some aberrations or some, let's say, scattering on the optics and so on, you may actually get some let's say, rugosity. But at the length scale of lambda of a single site, this is really clean. And it's in that respect different from what you have in solids, where you always have some defects or some phonons. Well, if you don't really like put a lot of liquid hydrogen to cool down, liquid helium to cool down your system. Okay, so this is the most simple one. Another simple one which is often used in practice is actually not to use one wavelength, but two wavelengths. But they don't, each other does not interfere with the other. And this allows you to create, so you have, let's say, lambda, for instance, and 2 times lambda, which we call the superlattice. And then in that, so once again, I'm saying you have one pattern at lambda and one pattern at 2 lambda, and they don't interfere with each other. But you sum the two intensities, and when you change the relative intensities, you can go from, for instance, from creating balanced double whale structures. And this, just to give you one example, if you want to study some Josephson physics between 2 lattice sites, you can have a repetition of many 2 lattice site systems, because this big barrier here may be very large, so that atoms are not tunneling through this one. So you have like all these 2 sites which are isolated. Or you can also have tilted double whales, which of course, may allow you to have one atom here, putting it back on the left, for instance. I think I will show some examples where we can use this type of superlattices. So this is 1D, but of course we can put an optical lattice in more than one axis. So by the way, this is another review. So this one is kind of old as well, but once again, it's nice to. There are some nice basic physics about optical lattices that you will find in this review paper. So in that case, what we are doing is putting 2 counterpropagating lasers. And what we are doing is, once again, we want to avoid interferences between the different axes. And so what we do, so you have, of course, a term which is, let's say, kx. You will have a term which is ky, okay, the interferences of the 2 beams along kx, the interferences of the 2 beams along ky, and then you will have a term in the interferences that, of course, will correspond to the cross interferences of one beam along x and one beam along y. And if those 2 guys have a frequency which is different, large enough, then this term will average over time to 0 for the atom. So let's say you have your atom. It has a given recoil energy. You have some energy scales, some other energy scales in your problem, the energy scale associated to the atom moving or things like that. And what you want is that this guy oscillates very fast on all those time scales. So that then you can just, on the time scale which describes the dynamics of your matter wave, of your atoms, you can average this term to 0, and then you don't have cross interferences. So this typically in the labs, we use like, let's say 10, 100 megahertz frequency difference between the different axes. Yes?
Why you can't use two perpendicular polarization?
You can also use two perpendicular polarization. You have more for difficulty when you go to the 3D one, 3D case. And then it's always good to actually not rely on having a perfect linear polarization, or let's say two perfectly orthogonal polarization, because this is extremely difficult in practice to realize. I mean, you can realize that up to a certain extent. Let's say if I give you a polarization cube, and then you say, well, on this arm will be linearly polarized vertical, this one horizontally polarized. Well, first of all, the reflection is much better polarized. The transmission is not perfectly horizontal. You have a bit of vertical left. And in any case, it will be always, there will be always a finite polarization, joint polarization. So if you detune, you avoid having this issue. And so we can generalize that to a 3D situation to create a 3D lattice, once again, not relying only on... So let me say that we also use, I mean, often, linearly polarized lattices with orthogonal polarization if you want to create 1D lattice. We also use that. But still, it's better to make sure that everything averages what is left. Okay. So a bit more exotic ones. For instance, you can add a phase difference between what you have in one direction and the other direction, and depending on the phase difference, you will realize different structures, which allows you to play a bit with a kind of crystal that you want to realize. If you use 3 beams, you will create some honeycomb or some triangular optical lattice structure. Once again, this is type of physics that you can play with. You can also, this has been done recently by colleagues in Cambridge, use 4 different beams to create like a 8-fold rotational symmetry, and this realize a quasi-crystal. So you don't have a real periodic system, but it's self-similar, and this is a picture that they took in the momentum space, and when you see the self-similarity. So I'm not, I don't want to detail those things. It's just to give you the flavor that, well, there are many situations that you can study. You just play with the light, and it's really easy. You just put some light, get the interferences you want, and you can realize many structures. You can even, and this I think will be, most probably will be touched next week, you can even think of having a dimension. So this is a real optical lattice, and in another dimension you play with internal degrees of freedom of the atom, and which is called the synthetic dimension, which allows also to do some other type of physics. So in that case it was about topology, which will be covered by Monica next week. Okay. Oops, sorry. So let's stop here about the structures. And now I would like to, so this was like just to give you a flavor about what is an optical lattice and type of structures that it can create. Now what I would like to do in the remaining time is to discuss the situation of a pulsed optical lattice. Okay? And from next week we will study a stationary one. So what do I have in mind when I say a pulsed optical lattice? Well, what I have in mind is that you are creating a lattice and you have a finite time of interaction, rather short. Short time of interaction of your matter wave with the lattice. So this can be either you have your atoms and what you do is you shine some light. So this is the light of the lattice just for a short time. Right, let's call that tau. But you can also think of having well, sorry, it's a 0 here. You have a standing wave, and you have like an atom jet that cross the lattice also for a short time, right? It can be either way. Even you switch on the lattice or you have the atoms flying through the lattice. Okay, so the first situation that I want to describe is that where the duration tau is much smaller than any other energy scale. Well, inverse energy scale. Well, any other time scale of the dynamics of your atom. So that why I'm saying this is because then on the time scale tau, I would say that the Hamiltonian is only this dipolar interaction. So that if I look at what happened to my wave function, I have only this term. This is time independent, well, or at least I'm taking it time independent, so no detuning between the two beams. And so what I end up with is having a time evolution, so on this very short time scale, right, where I can discard all the other terms in the Hamiltonian, so I'm only keeping that of this flashed optical lattice. What I have is a phase imprinting. So I'm just like changing the phase of this wave function. Of course, in particular, I mean, tau has to be much smaller than the time scale, for instance, for the density to change. So if you have a Bose-Einstein condensate, this would be typically the chemical potential of the atoms. Right, so tau is much smaller than, let's say, time scale for density, for changes of density. Okay, so in this pulsed situation, very short, yes?
So I did so this dipolar potential, you are imprinting a modulated phase across your...
Yes, yes.
Okay.
You know, what I'm doing is I'm flashing a potential, so in that case, like a light potential and an optical lattice, on a very short time scale with respect to all the other dynamics. Okay? And so the only thing it may do is this type of phase imprinting. So this actually was used, well, something like 15 years ago. It was used, and it's still used nowadays, to imprint some peculiar phase pattern onto a wave function. In particular, if you want to create things like vortices or this type of phase-dependent phase velocity, right? Because I don't know if you're familiar with that, but if you have, so the velocity, I can write it h bar over m times some, if you have a phase, a gradient of a phase gives me a velocity field. And so you can use this type of techniques, shining an optical light for a very short time in order to induce a phase gradient on the wave function and therefore change the velocity field. So this is quite a relatively popular technique. So of course, there is one thing that that I should make sure of is that, let's say, if this potential is of the order of V naught, what I want is that this term over the time scale of interaction gives me a phase shift, right? I mean, I want that V naught over h bar is something of the order of pi. Why I'm saying this? Because if I fix V naught and I put tau much very small, so that this term is much smaller than 1, well, basically, of course, I have not changed anything. Okay? So you have a condition on having tau short so that you don't modify the density and only imprint a phase. But of course, you need tau not to be completely negligible because otherwise you don't change anything. Okay, so what we have for our dipole potential was V naught, so I write it sine, well, 1 plus cos 2 kx should be divided by 2 like that. Okay, the sine square should be, minus is better. And so what I have so I will put this first term like this is a constant phase. And then I have this E V naught, let's say tau divided by 2h bar cos 2kx times I 0. And I can take the Fourier transform of this guy, exponential of cosine. This amounts to having Bessel's functions, which, so therefore, this writes if I, so I have I to the power n, I have a Bessel function order n of this argument v0 tau, is there the factor 2? Yes, 2h bar, exponential I to kxn, up, phi 0. And so if I have, for instance, if I assume that at time t equals 0, I'm in a relatively well-defined momentum state, let's say that I have an initial momentum p naught, and I'm, let's say, forgetting about the width and so on. So what will I end up with? Is giving a momentum, and so I get 2kx times n to the atom. So what I'm doing, I'm coupling the initial state to an infinite number of discrete states in momentum. Why is it? Well, once again, keep the picture. I do absorption, stimulated emission. I get a 2h bar k. And so I do that, and I can do that n times. So especially if tau is much smaller than the time scale associated to the recoil energy, it means that I'm not resolving the different energy scales associated to these different states. And so I can really couple to many states, to many momentum states. And what is the amplitude of the coupling? It's this Bessel function here. So this is called Raman-Nath so regime of diffraction. So of course, I mean, you can also draw an optical analog, right? It's this is like you have, especially if I say that I have a given initial momentum, well defined. I mean, this is like analogous to having a plane wave in optics that you diffract onto a periodic structure for a very short time. And then it gives like peaks of diffraction at many momenta, which are separated and are given the momentum separation by, of course, the period of the lattice. And so this is what can be seen in the experiment. So the first time it was done with in 86, so 86, sorry. So before having Bose-Einstein condensate. So this was actually it was an atomic jet. And in order to have a relatively well-defined wave packet in momenta, at that time you have a jet that was flying very fast, but with a very small momentum dispersion transversally, and you would shine the optical lattice transversally. And what you see here are different times of interaction tau, which is the argument of this Bessel function. And in dashed, you have the prediction given by this Bessel function, and then in solid line, it's what has been measured. So you see that you couple different components, and that it works relatively well and well described by this type of regime. So it's not. So this was the time when people were doing a lot of, let's say, matter wave optics somehow. But I mean, we can still use this type of approach. For instance, if you want to calibrate what is the amplitude of an optical lattice, you can pulse this optical lattice and you measure the time dynamics of these different components, which is described by these guys here. And if you adjust them, then you can calibrate what was. I mean, you measure time. This is what you set in the experiment. You measure this coefficient because this is the number of atoms you diffract in the different peaks. The only thing you don't know is V naught. And so this allows you to calibrate the amplitude of your optical lattice. So this is something one can do. And you see time scales are like a few microseconds typically, which is much shorter than the recoil, which is a little bit less than a millisecond. Good. It's fine? How much time do you have left? Sorry?
20 minutes.
Ah, okay, perfect. No, I had a second. I was like, why? I'm already 10 minutes over, but no, oh, perfect. Okay, so this was one pulsed lattice, pulsed very fast. Now there is another situation which actually I understand that was also touched by Frank somehow. Which is, I will still pulse the optical lattice, but now on a time scale which is, let's say, comparable or a bit larger than that associated with the recoil. So typically what I'm saying is that now I'm able to do energy resolved measurement of a different momentum scale that I'm coupling. Yes?
I have one last question to the sketch. So these are for different tau, right?
Yes, if I remember correctly, yes.
Okay, and which are for longer tau and which are for shorter tau?
I believe that it was going from shorter tau to longer one there.
Wasn't it like we would get more, we would couple to more momenta for shorter tau?
Well, at tau, so duration equals 0, I'm sure that you couple to 0 momenta. So there must be a short time duration, tau, for which you will start coupling to other states.
Yeah. Okay, so firstly it becomes like more states and then it goes down again.
Exactly.
Thank you.
Okay, so now I want to consider energy resolved measurement. And so this actually is related to Raman transitions, which you have talked about.
Yes.
Okay. So, well, sorry, I was not there to know exactly what was done. So in Raman two-photon transition, well, actually, you mentioned it this morning, and I don't remember what was the, let's say, I have a ground state 1, a ground state 2. So I have two different internal states that I can differentiate. And let's say this one has a momentum P, and so this one gets 2h bar k. Right? It do this two-photon transition, and here there you have the excited state. Okay, so this is Raman two-photon transition. I will not talk about that. What I want to describe is the same situation, but where I'm ending up in the same ground state. So there is no change of internal state. I'm just staying in exactly the same state. Okay. So now, if you want to do that, and because I'm saying that I do resolve the energy, when I do the two-photon transition, I must conserve energy and momenta. So the configuration I'm interested in is the following. Ah, yes, well, okay. I forgot one thing. I wanted to mention the fact that okay, well, but this you've done it, right? When you do Raman transition, you have a coherent coupling between these two states. I mean, you can also adiabatically eliminate this E state and get an effective Hamiltonian for these two guys only. And so therefore, you can, depending on the time scale of the coupling, you can transfer the population from, let's say, one state to the other and realize, so what is shown here, this is the probability to actually go in this state as a function of the duration of interaction. So you go from 0 and you can transfer 100% and go back. And so this is the way of having something which is like, sorry, so this is in French, which is a beam splitter. which means that you have half a chance of changing this state to this one, or a mirror where you directly change one to the other. And this is the tool to do atom interferometry, which was mentioned this morning with this Raman transition. Or you can also do, this was done actually in our lab at Institut Optique. You can use this interferometer to revisit some quantum optics experiment. I don't know if you've heard about Ongu-Mandel experiment. The idea is in the historical one optics, you send two photons on a beam splitter with exactly the same mode and at exactly the same time, and you have these destructive interferences of getting one photon on the output and the other on the other output. So you always get the two photons on one side or the two photons on the other side. So this was also realized with an atomic matter wave. Okay, so but this is things that you have already kind of heard about. And so what I wanted to discuss in the few minutes left, it's this situation, as I said, where I'm once again, I'm realizing an optical lattice. So you see that I'm sending one beam here, one beam there. So I will have an optical lattice in this direction here. This is the glass cell where you see the atoms in blue. And I have, let's say, transfer momentum K1, K2, and a frequency difference, omega 1, omega 2. So I have a moving lattice. And the question is the following. So, of course, I will transfer a momenta. Well, here I'm missing the angle, sorry. So, of course, it's the projection. Well, okay, they cancel anyway in the other direction, so it's fine. So typically, what I'm doing like that, when I do the two-photon transition, if I want to stay in the same internal state, so here I have what I've written Q. Okay, so I'm giving a momentum Q to the atoms. And I have this energy difference, which comes from having this moving lattice, which I must also consider to be satisfied if I have a time scale which is long enough to resolve those energy scales. So what will happen? Well, what will happen is that you can write this probability of actually doing this two-photon process through the lattice in this way. So let me walk you through this, what I've written here. So imagine that the atoms are in initial state phi I. Okay. What I'm doing then is I'm removing one particle with momentum k, and adding a particle with momentum q minus k, which means I'm transferring a momentum q. Okay? And then I end up in a final state. So this is about momentum conservation. So this is with, given, I've taken here a given thermal distribution of initial state with energy EI. And I also need to conserve energy. So this energy transfer h bar omega must be equal to the difference between the initial state and the final state. Okay? And this thing here is nothing but the dynamical structure factor, which you may already have heard about, which is a typical quantity that one measure in condensed matter, for instance, by doing neutron scattering. So what you do in neutron scattering is you have your, so for instance, in this experiment, it's on superfluid helium. You send a beam of neutron, and the neutron arrives with a given momenta, and it is, one way of saying it is, the neutron is deflected, so it changes its momenta, but it also changes its energy. So in the end, what the neutron has done is to deposit in the superfluid helium that you consider, a given momenta, and a given energy. Okay? And to that, well, you need to have energy which is conserved and momentum transfer which is conserved. And so, of course, not all the states can allow you to do that. So why is it interesting? Well, because, for instance, you can measure what I think has been discussed by Michael, which is the spectrum of weakly interacting BEC. So weakly interacting BEC, when you treat it in the Bogoliubov description, what you find is that the spectrum, so this is energy as a function of momentum, it's not this dashed line, which is h bar square k square over 2m, that of a free particle, but it's this solid line here, where you have at low momenta a branch which is linear, which is phononic, and then end up at, let's say, momenta which are larger than the inverse Healing length, having a free particle spectrum k square again. So these points here are not numerical points, it's a measurement which was performed 20 years ago. And the way one can understand this type of spectra is by saying, well, okay, I start with a BEC which is at 0 momenta, so it's at rest. And then I shine this moving optical lattice which transfers a momenta and an energy. So therefore, I'm trying to create an excitation in this interacting BEC. Well, when do I have an excitation? Well, I have an excitation only when momentum transfer and energy transfer corresponds to the dispersion relation. Which means that if I have this, let's say, dispersion relation, I will write it K. If I transfer a momenta Q, then in order to be able to deposit an excitation in the system, I must give that much of energy. If I give another energy, I will not do anything to the system. It will not be resonant. And so therefore, I mean, this is nothing but this delta function here on the conservation of energy, which therefore allows you, because this guy is a constant, it allows you to plot this energy as a function of the momentum transfer. So you get the radiation dispersion of your system. So this is called Bragg diffraction. Which is rather different from this Raman-Nath regime. So this was actually very much used at the beginning in our community. It somehow was used a bit less over the past years. But now it's becoming, again, something which is very much used. And I would like to show you two other examples which I think are really interesting of this using this Bragg spectroscopy. So once again, you are shining like two laser beams, create an optical lattice which transfer momentum K and an energy omega. So what has been done in this experiment, so this is in the group of Chris Vail in Australia. What they've been doing, you see well, we don't see it exactly, but the angle of these two beams is actually relatively narrow, relatively small. So what you end up with is a large spacing. And what they wanted is to look at a transfer of momenta which was, I mean, for the experimental parameters, relatively large in the following sense. They wanted to study the physics of what happened when you put two fermions, so this gas of fermions, which interact, and you bring them close together. So if you want to study this physics that happen at short time scale in position, this actually corresponds to looking at large momenta components. And I'm not, let's say, explaining you better than that, but So one quantity of interest for this, let's say, contact interaction is so-called tense contact. It's of interest because it characterizes the type of many-body system you have. And so what we did here is use the Bragg spectroscopy to measure the large momenta components. Okay? So looking at the dynamical structure factor at large momenta. And from that, we could extract this information about tense contact. And so why is it interesting? Well, so these blue points are the measurement. And all the other things are, well, some measurement, which were, I think, this 32 reference, which were very much scattered, as you can see. And all these other lines are theoretical predictions. And before this experiment, it was very much debated what was the correct model and what would be the one best describing this type of strongly correlated fermions. And as you see, I mean, clearly the data points exclude some type of theoretical prediction. So it really allows you to go in the lab, simulate a system of strongly interacting fermions, do the measurement, perform the measurement, so using Bragg spectroscopy in that case, and get an answer. So I think it's really much in the vein of using optical lattice, so in that case to probe the system, and do some kind of simulation and let's say try to understand which is the best model to describe the physics which is at stake. Another experiment that came out this year, which I think is really beautiful. This was performed in Hamburg, Germany. So it's again interacting fermions. So what they are doing there is they produce this disk, which is really a two-dimensional system. So you have nothing in the third direction. So it's tight enough that every dynamic is frozen in the third direction. So it's a two-dimensional system of fermions. And what they've been looking at, once again, was to measure this dynamical structure factor. So trying to probe whether you can excite the system by transferring a given momenta and a given energy. And so in blue, in these two graphs, what you have is how much excitation you can create once you change the momenta. So this K0 is the momentum transfer of a Bragg spectroscopy. So it's in unit of the Fermi wave vector here. And what you have here in vertical axis, it's the energy, which is here expressed in terms of velocities. So what you see on both graphs is that you have no excitation below this threshold here. All the excitations are above. Okay? And so the reason why they put this energy scale in velocity scale is because they wanted to put this line here that corresponds to the critical velocity, which you expect associated to the superfluid properties if your gas, the 2D gas of interacting fermions, would be superfluid. So what did they show here? Well, typically what they show is that below this critical velocity, which we want to associate to superfluidity, there are no excitations. And so this top graph is performed in a molecular BEC regime. And so you have typically phonons type of excitation. And this is in the BCS regime. But you see that everywhere you have no excitation below this critical velocities for superfluidity. So this, let's say, demonstrates that indeed the 2D gas of interacting fermion is superfluid. Okay, so this I find, I guess it's a nice, I find it another nice example of this Bragg spectroscopy. So I think I will stop here and, well, answer questions if you have any. No, I've lost all of you? So was it too slow? No? Okay. Too fast? Okay, good. Well, thanks if you don't have questions. See you later then.